So the problem is now we have implicit polymorphism with slight changes to the two typing rules. So the generalization rule goes if expression E has a type U and alpha is not used in typing context gamma, then we can generalize it. We can generalize the type U to this polymorphic type. So typically, when you have this typing judgment and some type variable, you collect all the type variables. So for example, this is alpha arrow beta, and then you test if this type variable alpha is used in gamma. Assume that alpha is already used in typing context gamma, and beta is not used. So beta is fresh. So that is, beta is not included in free type variable of gamma. Then what you do is apply the generalization rule and then introduce it for all beta only. You don't want to introduce it for all alpha because alpha is used in gamma. And you'd like to apply this generalization rule aggressively. Whenever you can apply generalization rule, do apply this generalization rule. In this way, you don't run the risk of failing the whole type reconstruction. The type reconstruction might fail later when you analyze the surrounding context. And in order to minimize the chance of failing the whole type reconstruction, you want to apply this generalization rule aggressively. And the specialization rule says expression E has for alpha U, and you may instantiate alpha to monotype A. And here we do not check the validity of a type A because you may introduce as many fresh type variables in this monotype A, but that's fine because all these type variables are assumed to be valid. So this is the system. Now let me show you one more example of applying this type reconstruction algorithm. The example is an empty typing context. We have let f lambda x dot x. So we use this identity function, polymorphic identity function, which is bounded to this variable f, and we apply f to f itself. So the question is, what is the most general monotype that we can assign to this let binding? And this example is going to illustrate the use of specialization rule. Let's see how the type reconstruction goes. First, we have to figure out the most general type that can be assigned to this identity function. And from the previous example, we learned that under empty typing context, this lambda x dot x can be assigned for all alpha arrow alpha. So to give the details, then what happens is we can assign alpha arrow alpha to this lambda abstraction with this assumption. Now remember that we want to apply this generalization rule aggressively. Whenever you can apply this generalization rule, do apply this rule. So in this case, alpha is found in the resultant type. So alpha is here, and here, but it's not found in the typing context. So we can apply generalization rule. So apply generalization rule, and we have this polymorphic type, which is actually the most general type that can be assigned to this lambda abstraction. Now it's time to test the type of this application. F applied to F itself under the typing context. This one, F has a type for alpha arrow alpha. So first, let's consider the argument because we have to first decide the type of the argument. Otherwise, we will not be able to find the type for the first instance of a variable f. So let's consider the second one under this typing context. So under typing context, this one, what's the type of this variable f? And this variable f should be assigned a monotype. In other words, this one must be assigned a monotype A because the first f is going to have a function type. So its type is a monotype A1, arrow A2. So you cannot leave the polytype here for the second variable f. So in the end, we will assign some monotype A1 to this function f, this variable f. So monotype to this variable f, and another monotype A1 arrow A2 to the first f, and the final answer will be some monotype A2. So the conclusion here is the second f, namely this one, must be given a monotype, not polytype. You don't want to leave for all alpha, alpha, arrow, alpha here. You have to specialize it to turn it into a monotype. So under the same typing context, f has this polytype, and it's time to apply specialization rule. But the problem is, at this point, we have no idea what type this type variable alpha should be instantiated to. We don't know because we have not analyzed the surrounding context yet. So inside this typing derivation, we cannot decide the type of this variable f. We cannot find the concrete type, the best type for this variable f. So our choice is we just don't know the type that this type variable alpha should be instantiated to. We simply don't know. Therefore, we just leave it as a question mark. So something like, we don't know. It's something like a question mark or a question mark. And our notation for this question mark is, let's introduce a fresh type variable beta here. Notice that we apply the specialization rule, but we do not test the validity of this type variable beta, because this type variable beta is guaranteed to be valid. It's automatically valid. Every type variable we introduce is going to be valid, so there's no need to test its validity. So what happens here is, let me summarize. What happens here is we have to convert this polytype to monotype for the reason that it is going to be passed as an argument to a function. So it must have definitely monotype. So let's instantiate this type variable alpha to a monotype. But the problem is we don't know what monotype this type variable alpha should be converted to. We don't know. But that's fine because we can just leave the question unanswered by introducing fresh type variable beta. Now, f has beta arrow beta, and then the first variable f is going to have type. So what happens is, so we learned that the second f has beta arrow beta. So perhaps the first f must have type beta arrow beta arrow beta arrow beta. And so we will see another example of applying the rule, specialization rule. So under the same typing context, we specialize. So this is polytype, and f has this polytype, and we specialize this alpha this time to beta arrow beta. Now the first f has this type, the second f has this type. So by the application rule, f has a type, beta arrow beta under the same typing context. And finally, the whole left binding expression is going to be assigned type beta arrow beta. So we introduced a type variable beta, which has not been instantiated to another concrete type. If the whole expression, this left binding, is applied to integer 0 in the surrounding context, then later we will discover that beta should be equated to type int. But when we consider this left binding in isolation, there's no way to fix the type variable beta. But that's what is left. This is what will be taken care of the type reconstruction algorithm. So this is how we use specialization rule. So the lesson here is, whenever you can apply generalization rule, do apply the rule aggressively, as exemplified by this case. And whenever you apply specialization rule, don't be afraid of introducing fresh type variables, because every fresh type variable is guaranteed to be valid. And later we can discover more constraints on this type variable beta. So for instance, later we might discover that beta should be equated to int, something like this. So now we have finished formulating the problem. The problem is, we have this implicit polymorphism with two slightly modified rules, this generalization rule and specialization rule. And we'd like to now devise a type reconstruction algorithm. So the type reconstruction algorithm is actually called algorithm W. Algorithm W, and it is actually a generalization of the original problem. The original problem is given a closed expression E or a program. It's a program, so it has no free variable. It's closed. We'd like it to find the best type that can be assigned to expression E. Because this is a complete program, there's no reason to assign polymorphic type. So the best monotype should be discovered for the given expression. And this is the final problem, but it turns out that we have to generalize this statement, the problem. So the algorithm W generalizes the original problem, and what happens is, under if this algorithm W takes as input a pair of typing context and expression E, and returns something called type substitution. This is called type substitution, and the monotype that can a monotype that can be assigned to expression E. And of course, this monotype is going to be the most general type that can be assigned to expression E. And the idea about this type substitution is, this typing context, the gamma, contains lots of type variables. So for example, it might have X. For example, this typing context, gamma, might have this type binding. F has a type alpha arrow alpha. And the expression E might apply, for example, F to integer 0. And then this type reconstruction compares this type binding against this expression, and then discover that alpha must be equal to int, otherwise this expression fails to type check. So the only way to get the whole expression type checked is by assigning int, concrete type int, to this type variable alpha. So as seen from this example, this algorithm W might generate lots of equations. And that's precisely this type substitution. In this particular example, it will generate the type substitution int for alpha, which basically says that alpha must be equal to int, something like this. So by analyzing the type construction, the typing context gamma and expression int, this algorithm W will generate lots of constraints, something like this. And this is called type substitution. So first, we needed to formally define type substitution. So let's do this. So what is the type substitution? So type substitution is basically mapping from type variables to monotypes. So type substitution S is defined as either identity type substitution, which we write ID, or singleton type substitution, A for alpha. So this is basically something like this one, int for alpha, which means that alpha must be set to integer. When we introduced type variable alpha, we did not know what concrete type this alpha should be equated to. But later, after analyzing more context and more expressions, we discovered that alpha must be indeed equated to type int. So we generate type substitution like this one. So this is another way of writing alpha must be equal to type A. But the typing context might contain lots of type variables, so we should be able to provide some way of applying type substitutions to multiple type variables. So to this end, we introduce another component, which is composition. So this is the composition of two type substitutions. So the idea is S1 composed with S2 is we first apply type substitution S2, and then we apply type substitute S1, just like a function composition. If you have a function composition f composed of g, you first apply the function g, and then you apply function f. Similarly here, type substitutions, we first apply S2 and then S1. And this makes sense because type substitutions are so nothing more, nothing less than just mappings from type variables to types. And it turns out that this composition is associative, which means that S1 composed to S2 composed to S3 is indistinguishable from S1 composed with S2 composed to S3. So for simplicity, it's fine to write S1 composed S2 composed S3 because this composition is associative. Now let's formally define this as type substitution operations using type substitution. So basically, we'd like to apply this type substitution as to U. So this is apply type substitution as to polytype U. And let's see the actual definition. So there are three cases of type substitution: identity, singleton type substitution, and composition. First, what if the substitution is identity substitution? Then by definition, identity substitution performs nothing. So the result is, of course, U. Now let's consider the second case, A for alpha. If the type is, for types, so this is the definition of types. A is A arrow A or type variable alpha, and U is for all alpha U or A. So let's consider this case. If the type is alpha, then literally you substitute A for alpha in alpha, so therefore the result is A, of course. But if the type variable is different, so here alpha is not equal to beta, then these two guys are different, so it has no effect. So we leave beta as intact. What about the function type? In this case, we just propagate the substitution, type substitution, into the individual components. A1 for alpha, B2. Now finally, we have to deal with this polymorphic type. So A for alpha. Suppose that this type variable in this type binding happens to be identical. Then what happens? Just like the ordinary substitution from lambda calculus, it has no effect. So it has no effect. But what happens if this variable is different? So here, beta is not equal to alpha. In this case, we'd like to propagate this one into the polytype. So it's going to be A for alpha U. But just like the ordinary substitution in lambda calculus, you have to be cautious about the chance of variable capture. So in order to prevent type variable capture, you have to make sure that beta is not found in the set of free type variables of A. So with this extra condition, you can always avoid type variable captures. And if this condition is not satisfied, then you can always rename this type variable beta, similarly to alpha conversion in lambda calculus. So, but the focus here is not on how to deal with the variable captures and how to apply renaming, how to apply alpha conversion, how to rename the type variable. So it's not our focus. So let's just assume that there's a proper definition here for renaming type variables. And finally, what's the definition of substitution S1 composed with S2 applied to type U? So we, just like a function composition, we first apply type substitution S2 to type U, and then the result is used in this substitution, in this application. So this is the formal definition of applying type substitution S to polytype U. So now we have this formal definition. Now, let's first state the soundness of this algorithm W before we develop the concrete algorithm, the details of the algorithm. So, what's the meaning of the result of this algorithm? So what's the meaning? So we'd like to state the soundness of this algorithm W. So suppose that we have this result. What that means is that this type substitution is dealing with all the type variables inside this typing context gamma. So what that means is that you apply type substitution S to every individual component in typing context gamma. So for instance, if gamma is x1 has a type u1, x2 has a type u2, and so on, then S applied to typing context gamma is just x1 has a type, S applied to u1, x2 has a type, S applied to u2, and so on. So the definition is straightforward. So under this modified typing context, expression E has a type A. So this is the soundness of algorithm W. Or you can think of it as the specification of this algorithm W. And we will actually now develop the details of the algorithm W. But before we develop the details, before we develop the algorithm W, let's consider several examples to familiarize ourselves with the basic idea in algorithm W. So here are several examples. The first example is, let me erase all this one. So the first example is, what should this algorithm return for this given input? So the current typing context is this one. Alpha has a type, variable x has a type alpha, and we'd like to find the type of this x plus 0. And the idea is, in the beginning, we don't know the concrete type for this variable x, but later we discover that x is added to integer 0. So at which point we can find a new constraint, which is alpha must be int, for the reason that otherwise this expression would fail to type check. So the only way to get the whole expression to type check is by equating type variable alpha with concrete type int. So we obtain a new fact about this type variable alpha. So the result will be alpha must be replaced with concrete type int. That's the only way to type check the whole expression. And then the whole expression will have a type int. So we haven't developed the algorithm W yet, but this algorithm W would return an answer like this one. Then let's analyze the result again with respect to this soundness. Let's apply the substitution to this typing context. Apply the substitution to this typing context. Then we obtain x has type int. And under this typing context, expression x plus 0 has type int. So notice that the final type, the type of the expression, contains no type variable alpha. And it makes sense because you have already applied the type substitution as to typing context gamma. So therefore, this type substitution S has no effect. That is, if this is the case, then S applied to A has no effect. S has no effect on type A because we have already applied the type substitution S to typing context gamma. So this is going to be equal to A. Like this one, there's no point in applying this substitution to the resultant type int because it has already been applied. So we see the equation holds in this example. So that's the first example. The second example is, this time the typing context is empty and we'd like to test this expression. So the algorithm would proceed in this way. First, we'd like to find the type of this variable x. But before analyzing the body of this lambda abstraction, there's no way to fix the type for this variable x. So we leave the question unanswered. So that is, we introduce a type variable alpha, and we assume that x is a type alpha. So this is a fresh type variable. And later, we discover that alpha must be equal to int, because x is added to 0. And the algorithm W accumulates all the type substitutions that have been generated along the way. So what happens is, you actually return this substitution. And under this equation, the whole lambda abstraction is going to have a type int arrow int. This example might well look confusing, because if you look at the result, the final answer has no type variable, but type substitution has this fresh type variable alpha, and in the beginning there was no type variable alpha. But this is fine, because this algorithm W collects all the type variables introduced during type checking. So a type variable like alpha here is the one that has been generated as a fresh type variable. So there is nothing wrong with having a type variable alpha here. It does not appear in the argument, and it does not appear in the resultant type either. That's fine. But that's just the nature of this algorithm W. And finally, what about this one? The typing context is empty, and the expression is lambda x dot x. So first, we don't know the type of this variable x, so we have to introduce fresh type variable alpha, in which case the whole expression is going to have a type alpha arrow alpha. And we have not discovered any constraint imposed on this type variable alpha, so the type substitution is empty. We have not generated any type substitution, so this is empty. And the return type is alpha arrow alpha. So this example illustrates that the return type can contain fresh type variable. This alpha, we didn't have type variable alpha in the beginning here, but in the result, we have type variable alpha. So this is precisely an example of a fresh type variable generated by this algorithm W. So the answer is this one. So now we are really ready to develop the algorithm W, the details of the algorithm W, because now we have the problem statement. Algorithm W takes a pair of typing context and expression, and it is supposed to return a type substitution, monotype. So that's the problem statement. We have formally defined the type substitution here. And we also discussed the soundness of a W. This is the property that the algorithm W should satisfy. So in other words, a correct implementation or correct design of an algorithm W would satisfy this condition. So this statement characterizes the nature, the property of this algorithm W. And we have seen 3 examples. So now we are really ready to develop the algorithm W with all the details. And this will be covered in the next lecture.